In this video, we'll look at how to count significant digits and how to do calculations and report our answers correctly to the proper number of significant digits. What we need to always remember is that significant digits are digits that are measured. So when we are using an instrument to measure a piece of data, the significant digits are the ones that we read using the instrument. So firstly, there are 5 rules that we can look at, and there are a number of different ways of looking at these rules. Non-zero digits are easy. They're always significant, as rule number 1 shows us. It's the zeros that can be a bit tricky, and so there's a number of different scenarios that we want to look at. So first of all, when you have non-zero digits that are zeros that are between non-zero digits, those are significant. They've been measured. So if I'm measuring something that has a value of 40.07, in order to record those inner zeros, I need to measure the outside ones, the 4 and the 7. So this value of 40.07 will have 4 significant digits. I need to measure all of those. The zeros, which are merely used to fix a decimal place, are not significant. And we sometimes call these leading zeros. So in the number 0.052, there are only 2 significant digits. These zeros have not been measured. If you think about this value of 0.0552 being recorded on a scale, or any number for that matter, it increases from this side. So these zeros, although we've written them down first, they have not been measured first. Sometimes it's easier to look at a number in scientific notation. So if you look at this number as 5.2 times 10 to the negative 2, then you can see that the zeros that are not significant have disappeared. So if you're not sure, sometimes it's easier to put it into scientific notation. For the same reason that the 5 and the 2 are significant, if we have zeros after those, so after the decimal point, after a non-zero digit, those will be significant. So these 3 are going to be significant digits. So these leading zeros are still not significant, but what I'm saying here is that it's exactly 420, not 421, not 423, okay, not 419, it's exactly 420. So I've measured it. So there are 3 significant digits there. The number 32.0, so after the decimal point, after a non-zero significant digit, is significant. So I'm measuring it to be exactly 32.0. Trailing zeros are also not significant. So zeros that are after the non-zero digit but to the left of a decimal point are usually not significant. And this often, when we're talking about counting large amounts of things, this is when we see these kinds of zeros. So if I say there's 186,000 people that live in a particular town, I haven't counted each individual person. There is some kind of estimation that's going with that. So that's why there's 3 significant digits. I'm sure of the range based on the values that I'm giving you. 52 billion, I'm not really sure. It's very much an estimate. Now there are cases that are a little bit more tricky. So the number 100, I might want it to have 3 significant digits. I might say it's exactly 100. And I want to show that I've counted 100. And so there's a few ways to do it. You can put a decimal point after, so 100 point. That shows us that it's exactly on 100. Whereas the number 100 is more of an estimate. There were about 100. Okay? Or there was about 100 milliliters, or I needed about 100 milliliters of solution. Whereas in this case, I measured exactly 100 milliliters of solution. Another way to approach this to show the correct number of significant digits would be to put it into scientific notation. So the number 1 times 10 to the 2 only has one significant digit. If I want to increase that to 2 significant digits, I could report 1.0, and if I needed the 3 significant digits, I could say 1.00, and I could continue to add zeros if that's how many digits I've measured. Here's some quick examples. So here we've got some leading zeros. Those aren't significant. So here we've got 3 significant digits. When you've got a number in scientific notation, anything that's in the coefficient is significant. So this will have 4 significant digits. This is more of an estimate, 2.5 million. So I haven't counted them. There's 2 significant digits there. Whereas this is the number 1,000 that's been measured quite carefully to be exactly 1,000, is showing that we have 4 significant digits. This measurement here, 47.80 exactly, has 4 significant digits. 609, I've got that zero that is between 2 non-zero digits, so they're all significant at 3, and then 10 point, so it's exactly 10, so there are 2 significant digits. Now really what's most important is how we report our final answers when we have measurements involved. And there are different operations that we'll be doing with the data that we collect. We might be adding and subtracting our data, or we might be multiplying and dividing our data. The rule that we use for addition and subtraction is that the answer contains the same number of decimal places as the least precise measurement, the one with the fewest number of decimal places. So with these pieces of data, I've got 32.205, I've got 3 decimal points, 1.2, I've only got 1 decimal point. This is my least precise value out of the 2, so my answer needs to reflect that. My answer will only be able to be as precise as my least precise value. So my answer can only have 1 decimal point. To think about this so that you can understand it, you want to think about making these measurements with a scale. If I measured something on one scale and found it to be 32.205, so I'm using a very precise scale, and then I didn't have access to that same scale and I was measuring something else to be 1.2 grams, if I wanted to add those two together to know what the total mass, I could only be sure that it's going to be 4.4 grams. I can only be as sure as the scale that is least precise. Okay, so that's why we do that. When we're doing multiplication and division, what we're going to do is use the significant digits that we have. The answer will contain the same number of significant digits as the number with the least significant digits present in the original data. So again, this is about no answer showing greater precision than the original data that we had. So in this example here, I've measured a mass to be 60.37. I've measured a volume to be 34 milliliters. And you can see that my volume measurement is not as precise as my mass measurement. It's always based on the instruments that I have available. If I want to find the density of this object, I'm going to use density is equal to mass divided by volume. And when I do the math here, I can only report my answer to 2 significant digits. The reason being that my least precise value, my volume, has 2 significant digits. So I report my answer to that same number. So when somebody obtains my result, when I report that my density found in the experiment was 1.8 grams per milliliter, that reflects the precision of the instruments that I used to make those measurements. Now, one note, and this is important because oftentimes when we're doing calculations in science, we don't just have a one-step problem. We don't just do one calculation. We often will take one value and carry it forward to other calculations. When you're doing that, the best thing to do is to just keep all the numbers in your calculator if you can. If that's not possible, you want to carry at least one extra significant digit through your problems, so don't round too early. And at the very end, you're going to report your answer to the correct number of significant digits. Okay? This way, you'll ensure that you have the answer reported to the correct number of significant digits with the right level of precision.